Thank you very much, Dania, for the introduction. Thanks, Yamin, for making this event happen, and thank you all for being here. I'm pretty excited about this hackathon because now we are live, face-to-face. We can come together and physically work on the robots. I'm Ádám Wolf. I'm basically wearing 3 hats. One is with Takeda, where I'm working as a PhD student. I'm doing an industrial PhD. And that obviously means that I'm affiliated with the university, the Óbuda University of Hungary. And my 3rd hat is with SiLA, where I lead the robotics working group. So there we try to address some of the limitations and challenges with the state-of-the-art robots. And for that, we have to consider what robots are used for in the lab. The most traditional application is probably liquid handling, where you have gantry-type robots performing liquid transfers, and also some of them have internal manipulator arms. And then you have benchtop, more open, more flexible setups, like the Andrew Plus model. Another application area is sample transportation. Traditional form is stationary robots or benchtop robots. And a fairly new topic is mobile manipulators. But even this is currently being addressed by multiple solution providers. There are products out there. And they mostly share the same structure, the same anatomy. So for stationary robots, they are either SCARA-type robots or articulated robot arms with parallel grippers. Specifically designed for standardized sample carriers. Whereas the mobile manipulators are mostly wheeled platforms, either differential drive or omnidrive that can drive sideways. And they usually have some sort of computer vision to localize the handover positions. One limitation is that even these autonomous robots need teaching. So you manually have to drive the robot next to the station. You generate the map. You have to store this location and then detect the relative position from the robot's coordinate system to the marker. And then also move the robot arm manually to the handover site, so that the robot kinematics and this transformation between the marker can be closed, so to say, this gap in the graph, and then the relation between the marker and the handover site is ultimately stored. So with the working group, we are trying to address some of these limitations, and also in general we want to combine existing solutions as building blocks and also unify them and standardize them. So some of the milestones that we achieved during the previous hackathon, we worked on a reference implementation for a bridge between SiLA, which we consider a high-level protocol for communicating commands to lab devices and the robots. And we bridged this with the low-level robot-specific middleware robot operating system. This was one of the first milestones. And then I mentioned unification. So standardization really should mean that possibly many of the actors of the industry agree upon common protocols and common definitions. And with the feature unification endeavor, we try to address this. We, on one hand, work on a structure, a skeleton that should be capable of incorporating current state-of-the-art capabilities like sample transportation, but also future applications like complex interaction with lab devices and tools or even with humans. On the other hand, we identify candidates that already address some of these present state-of-the-art capabilities. And today's hackathon is an example of using some of these candidates, namely the labware transfer controller feature definition. And that brings me also to the structure, how we consider lab workflows, to how they can be broken down and decomposed hierarchically, so that we can also consider the level of abstraction that we expose with a SiLA interface in this case. So on the laboratory scale, we start by the experiment, the procedure, but that can be a part of an overlaying service. I think cloud labs or service labs were already mentioned during one of the previous talks. So a lab procedure has tasks that make up the whole procedure, and we distinguish between liquid handling and robotic labware transportation and supportive actions. So each task can be decomposed into subtasks, what we call. So for example, labware transfer consists of picking the container and placing it. Those are two separate parts. And then those consist obviously of motion sequences. So the robot performs a certain trajectory, and these sequences then can be broken down into motion primitives. So linear motions or joint motions or anything of that sort. And then on the hardware level, so really the embedded control of the robot needs to take care of how these motions are executed. So what are the joint angles and velocities that are needed for that? So when we want to unify the feature definitions, we have to look at the existing implementations and consider what level of abstraction they address. And we realized that there are different approaches. So some solution providers really just focus on the task level, the high level, you could say outcome-oriented definitions. But some also expose deeper layers for debugging or custom implementation purposes. So what we came up with is two categories. We also have a high-level outcome-oriented category where you prescribe what you want to achieve. So you want the sample to be transferred. Everything that's deeper level, more detailed than that, that goes into the low-level category. So we came up with this structure. Here you see some of the outcome-oriented categories and feature skeletons for cleaning, for device manipulation, even human interaction. And those are like really empty headers, placeholders for future implementation so that they can be inserted into the structure. Whereas labware manipulation is already something that's being addressed, and that will be the subject of today's hackathon. The low-level category contains features broken down into the subcomponents of robots. So if you consider mobile manipulators, they consist of a base, an arm, and a gripper. And you can define the low-level features broken down for each of those components. So for example, navigation, that relates to the base, obviously, and motion planning relates to the arm, gripping action, the end effector. Also, maintenance is an interesting category. There we have functionalities that are not really meaningful from the lab process perspective, but you need it to maintain the capability of the robot. Reference implementations was the next milestone, and one example of that was the project of Panna Zsaldos at our company. She worked with our Tiago platform and collected the building blocks consisting of navigation, marker detection, motion planning, and prepared the platform for SiLAfying it, so to say. Also at another company, a project is starting with a MIR and UR platform with a similar goal. And as I mentioned, today's hackathon will also focus on this, but with a simpler use case and not mobile manipulators, but stationary. So there, we don't need marker detection, we don't need manipulation. The positions are predefined. You only have to define the sequence of motions and also the integration interface based on the feature definition. Ultimately, we want to make the platform capable of incorporating new approaches, such as information representation to really make it plug and play capable, the integration without manual teaching, without manual configuration. And for that, we came up with the so-called laboratory automation plug and play framework. It's a conceptual framework at this point. And it aims to combine building blocks like communication based on SiLA, and we extend it with the information representation, the digital twin layer, what we call. And also we have to consider the low-level robot-related middleware, ROS-related implementations. So here you can see an important aspect, the information representation and how it should be a part of an online database, a global online database in the cloud that the vendors of each component fill with data. And that means that when you put your device in your lab, you set it up, the system fetches this information, instantiates the digital twin, and then the robot can start really operating the device. That is possible thanks to the fact that this also will include geometrical relations within the context of the device, of the component. The relation between the marker and the handover site should be a part of the digital twin prototype of the device, what we call. So coming back to the hierarchical distinction, I already showed this table about the process, but we also have to consider what type of languages are capable to describe each level of abstraction. So the procedure can be described on an abstract manner, so what we want to achieve. And this needs to be matched with the available capabilities of the components and grounded to the actual execution environment so that the laboratory process language can be really executed on a specific laboratory. And then for the devices on the liquid handler side, you have to specify the liquid handling steps, the scripts, and for the robot, you need a modular robot program that is capable of fulfilling those actions that you want it to do. On the control architecture side, we have something similar to what you would call the automation pyramid in industrial automation terms. Here, you, in most cases, have some sort of high-level management system or execution system. But also, you have a scheduler or orchestrator that interfaces with the devices via a communication protocol like SiLA. So the devices then have their dedicated PCs, both for liquid handlers, analytical devices, and for robots. And on these PCs, you have the high-level environment to program the liquid handling script, for example. And this level takes care of the SiLA communication towards the high level, and also takes care towards the low level of the communication with the embedded controller. So that can be a microcontroller of the device or a PLC of the robot. We also want to make the system capable of incorporating new advancements, so go beyond simple pick and place, incorporate the usage of tools, detection of objects, not on a marker basis, but on advanced perception or even tactile sensing. And there are research projects ongoing in various academical teams globally. Finally, I want to bring into your attention the SiLA Robotics Working Group. We have bi-weekly meetings. It's an open group. Everyone is free to join. You can participate in the discussions. There are, for example, ongoing exchange and ideation about workflow representation in a standardized manner. We talk about BPM and about PAML, and also what type of ontologies can be used to really make this plug-and-play setup possible. So the technical details about today's working group will be discussed with the team. I end my presentation here, and thank you very much for your attention.